Our discussion in the last video on transformers leads us nicely into the final topic of the chapter, which is on inductance. We'll also include a little bit at the end of this video on the energy due to magnetic fields. So here is what is going on. You have two coils. Let me actually move to the next slide quickly just so you have an idea of what's going on. So you have here two coils of wire right next to each other. If you have a changing current in one coil of wire, that's going to produce a magnetic field which changes the magnetic flux in the second coil and induces an EMF and thus a current in the second coil. This is something we call mutual inductance. A changing current in one coil induces a current in a second coil. The way we calculate this is that the induced EMF in the second coil is going to equal negative M, where M is known as the mutual inductance. It's a property relating the two coils to each other. And that's multiplied by the change in current in the first coil divided by the change in time. So again, the induced EMF in the second coil is equal to negative M times the change in current of the first coil divided by change in T. Notice that this works vice versa. So if you have a change in current in the second coil, that also induces an EMF in the first coil. And so that's kind of an interesting thing that happens in mutual inductance, where you have two coils next to each other. One coil has a change in current, which induces an EMF in the second coil, which changes the current in the second coil, thus changes the EMF in the first coil. And you just get a process that bounces back and forth between the two coils. Now we measure the inductance of a particular system. For example, this system here in this picture. We measure it in units of henries. Now, Henry was a scientist of electricity, Dr. Henry, a scientist of electricity right around the same time as Michael Faraday. It's one of his contemporaries. So we talk about inductance using his name as a unit, the Henry. And 1 Henry, you could either calculate that as a volt times a second divided by an amp, or that could also equal an ohm times a second. Now, this is the easiest way to talk about inductance, but there's something else that we need to talk about as well. Turns out that a changing current in a coil will induce an EMF in itself. And think about this. You increase the EMF, that changes the current in that coil. Well, that changing current then induces an EMF in the same coil in itself. So it's the exact same equation, but instead of talking about mutual inductance, which would be inductance between two coils, we have capital L, which is self-inductance, inductance within a single coil. That is all that we need to really cover in inductance. So let's switch gears and let's talk now about the energy stored in a magnetic field. If you go back to chapters 16 and 17, the author of your textbook talked about the energy stored in an electric field. And it turns out that the energy density, which I'll describe again for you in just a second, the energy density would be 1/2 of epsilon naught times the electric field squared. Very similar process here. Energy density. What on earth do we mean by energy density? Well, it's really hard to talk about the entire amount of energy of an entire magnetic field. So what we look at is a small given amount of volume, and we talk about how much energy goes into or comes out of that volume. Just how much energy is compacted within that single volume. And so that's why we call it energy density, the amount of energy per unit volume. So anyway, like I said, for electricity, that energy density would equal 1/2 epsilon naught times b squared. But for magnetic fields, the energy density would be 1/2 b squared over mu naught. Now, this is important because when we start talking about energy in an electromagnetic wave, which is in the next chapter, and we are now ready to talk about that, these two equations are going to come up again, and we'll be able to calculate the energy of an electromagnetic wave.